So I'm now going to move to a different example with some actual numbers to walk through this process of what we've been talking about as far as comparing models. So in this example, I want to examine the relationship between suicide attempt, which is the outcome, so whether or not someone has attempted suicide. So again, categorical, one or the other, they have or they have not. And depression and self-efficacy, two continuous predictors. So we've measured someone's depression using some form of continuous scale, their self-efficacy using some form of continuous scale, and we also know whether they attempted suicide or not, the outcome. So model 1 includes only depression. So the model with only depression predicting whether or not someone commits suicide is the smaller model in this case. So the -2 log likelihood is 210.98 with the degrees of freedom of 2. The second model includes both continuous predictors, and in that case, the -2 log likelihood is 206.25 with the degrees of freedom of 3. Now notice the smaller the -2 log likelihood, the better the model. So we already know that model 2 is a better model. The question is it a significantly better model? So in order to know that, what we need to do is subtract the larger -2 log likelihood from the smaller -2 log likelihood. Now, if the second model had a larger log likelihood, we wouldn't even bother, because at that point it's going to be a negative number, and that tells us the model was worse. We may actually want to find out by using the absolute value, is the model significantly worse, but there's no reason to add a predictor if we're not getting a better model. So we usually would only go through this process if a model with more predictors resulted in a lower -2 log likelihood. So again, in this case it did, so we want to ask, is this a significant improvement? So 210.98 minus 206.25 becomes 4.73. That is our chi-squared delta. That is the difference between the two models. Now, we need to get a degrees of freedom to see if this is significantly different. And again, that is the degrees of freedom of the larger model with more predictors minus the degrees of freedom of the smaller one. So in this case, 3 minus 2 equals 1. We then would just go straight to a chi-square distribution table. And in this case, a chi-square of 0.05, so a p equals 0.05 or lesser, at a degrees of freedom 1 needs to be a chi-square of 3.84 or higher. Since we have a 4.73, this was a significant improvement. We would want to use the second model. Once we actually have our completed model, we now need to ask the question of the predicted probability. So coefficients are going to be used to solve equations for the probability of any one person being in a particular group. And the y prime in this case, so us predicting whether or not they would be in a category or not, is going to be different than just using the regression equation. Because again, the regression equation without adjustment is looking for a continuous outcome. We now want a categorical outcome. So this is the basic equation. It is y prime, so our predicted group membership, yes or no, equals e, which is a constant, raised to u power. And u in this case is actually mu, but that is the power of our sample. And I will get to where we get that value and where we get the constant in a second. So what is the likelihood of stopping smoking? Predicted probabilities are computed to actual outcome to estimate the accuracy. So once we have the prediction, so for example, if we knew that y prime said there was a 75% likelihood that the person had stopped smoking or had committed suicide, and the reality was that they had, so their real value was 1, we predicted a 0.75% chance they were in 1, that means that the estimate error is -0.25. We were 25% away from the right answer. And again, that's just something we're going to do to try to get an idea of how good our probability predicting are. So we're going to go to the next slide and talk about how we actually predict using logistic regression. So given that the regression equation in this case, going back to whether or not someone committed suicide, the first thing we need to get is that u. So u in this case is the regression equation. So we have our constant, -4.2. We have our B weight for depression, 1.2, and we have our B weight for self-efficacy, 2.04. So we would actually want to solve for any one particular person based on their depression and self-efficacy score. And whatever that equation became, that is mu. That's what we're going to raise e to. E is a constant. It's 2.71828182845 ad nauseum. We can round it to 2.72. So we can use this to estimate the predicted probability that a person with known depression and self-efficacy scores will attempt suicide. And I'll run through a specific example on the next slide. So in this case, someone's depression score is 1 and their self-efficacy score is 2. So we're going to again solve for mu. Negative 4.1 plus 1.2, the B weight of depression, times 1, their score on depression, plus 2.04, the B weight on self-efficacy, times their actual score on self-efficacy, 2. That gives us negative 4.2 plus 1.2 plus 4.8. Add them together, we get a mu of 1.08. So that is the power we're going to raise E to, both on the top and the bottom of the equation. So in this case, we're simply going to calculate that out, and remember that E is a constant, 2.72. So 2.72 raised to 1.08 divided by 1 plus 2.72 raised to 1.08. So the top of the equation is 2.95, the bottom of the equation is 3.95. We divide, it equals 0.75. We would predict there's a 75% chance of this person actually being suicidal or having attempted suicide. So the predicted probability are compared to actual outcome, and in this case, again, 0.75 is what we predicted. Turns out the person had tried to commit suicide, and therefore our error rate is negative 0.25. So again, we said there was a 75% likelihood that they were in a category. The reality was 100% they were in that category, and that's the error. Now notice if we had predicted a 95% chance in that person being in the category of having tried to commit suicide, our error rate would have been only 0.05. So again, this is kind of just trying to get at how often are we potentially wrong, or in this case, we didn't predict strong enough. In other words, we should have been certain this person was in this category because they were, and we weren't. We were 75% sure that that's the category they would have ended up in. Logistic regression, once we have a complete model, does not have an equivalent of R squared. So if we're talking about effect size of the model, there's a few things we can do. The first one is McFadden's rho squared. It's often referred to as P squared, so rho squared, and it equals 1 minus the log likelihood of B divided by the log likelihood of O. So again, what we're looking for is about between a 0.2 and a 0.4 is good, and you'll go over how to calculate this based on SPSS readouts in lab. The problem with this is it tends to actually be a little fragile for less well-fitting models, and also it does not adjust for sample size. So the larger the model, usually the more confident we can be about an effect size, but McFadden's rho doesn't include that. Cox-Snell's R squared considers sample size, but tends to underestimate effect size. And again, I have the equation written here. And again, SPSS will generally give you these values as well. And finally, there's Nagelkerke's R squared, which adjusts Cox-Snell's R squared and is more suitable for better models. So which one do you use? You can use all three. You can use one or the other or the other. Generally speaking, if you've got a really strong model that's very accurate, I would use Nagelkerke's R squared. If you've got a moderate sized model, you may be underestimating how much you're predicting if you use Cox-Snell. If you've got a large model, you probably should be using Cox-Snell. And by model, I'm talking about the number of participants or N in your sample. There really is no right answer here, and a lot of times people will look at all three to try to get a better feel for how good the model is. Another easier way to do this is to skip the entire concept of R squared and just actually look at the percentage of correct classifications. In other words, just how often were you right? And this is simple mathematics. So you can go with your predicted scores by the actual scores. So in this case, 25 people had cancer and we predicted cancer, but 25 people had cancer and we predicted no cancer. 20 people had no cancer and actually had cancer, and 30 people had no cancer and we predicted no cancer. We simply calculate how often were we right. In this case, it's 55%. That might make a lot more sense than trying to come up with some other form of effect size. So again, there's just the equation for Nagelkerke's adjustment of Cox-Snell's. And again, I think I really want to just point out that there's a lot of different ways to look at effect sizes, and none of them have been agreed on by everyone that uses these techniques. I've kind of already gone over approximately when you'd use each of these. Just be aware that all three of them are trying to capture basically the same thing as R-squared. They're trying to give you percentage of variance explained. But since we're categorizing people into groups, honestly, percent of correct is probably a more likable and more reasonable thing to report. And again, just walking through the number of correct answers divided by the number of wrong answers. We can also look at odds ratio. Odds ratios are often used to estimate an effect size for a variable. And again, what we're looking at here instead of a straight percentage is, again, we've got the number of people that we correctly categorized versus the people that we didn't. And we simply run it through this equation. So A and D are basically our correct. So we had a smoker, we predicted they'd have cancer. We had a non-smoker, we predict they didn't have cancer. We'd multiply the number of people that were correct. Then we'd get the number of times we were wrong. We predicted no cancer, but they were a smoker, or we predicted that they weren't a smoker and they had cancer. And again, we'd multiply these, and then we simply divide. So smokers are 8 times more likely to get cancer than non-smokers, or people that are depressed are 8 times more likely to be suicidal, or those that are have high self-efficacy and a short history of smoking are 8 times less likely, or 8 times more likely to quit smoking. Whatever it was that you were testing, what this is what are the odds ratio. And it's another way to talk about effect size that makes a little more sense to the fact that we're categorizing people. I finally want to touch on ordinal logistic regression. This is a variation of basic logistic regression. It only differs that the outcome variable is ordinal rather than dichotomous. So it's 3 or more levels and they're ordinal. Instead of comparing category A to B, it creates cutoffs that compare various categories, A to B and B to C, or A to B and B to C. And again, this is with 3 categories. It could be more. It is not limited by the number of categories. The more categories simply create more complex analyses, as is almost always the case. So statistical assumptions, it does assume a linear relationship between the continuous predictors and the logic transformational of the outcome variable. Because it is ordinal, there is an order to it. At that point, we would expect some form of linear relationship, but we'd also not expect it to be normally distributed, which is why we do a logic transformation, and then we look to see if it's linear. If it isn't, we've broken one of the assumptions. The outcome variable is categorical, either dichotomous or ordinal, but if it's dichotomous, honestly, just run a regular, or you want to just run a logistic regression. You don't need to run an ordinal regression. It does not assume homogeneity of variance, and many of the other concerns that we have with multiple regression apply to logistic regression and, of course, ordinal regression. So I hope this kind of gives you a big picture of why we're using this. Most of this is going to come down to simply how do you run it and how do you interpret those outputs once you have them. So again, just kind of breaking down the differences between linear regression versus logistic regression. Linear regression, we're looking at the overall model fit indicated by an R-squared, the higher the better. In logistic regression, we're looking for overall model fit indicated by the log likelihood, specifically the -2 log likelihood, the lower the better. This can be converted to an R-squared, and we talked about the 3 techniques to do it. In linear regression, the coefficients indicate the amount of change in the slope of the equation due to the presence of the IV, and these are tested by t-tests. In logistic regression, the coefficients indicate the amount of change in the probability of a person belonging to a referenced category or not in that category, so one group or the other, based on their value in the IV, and this is tested by the Wald chi-square test. In linear regression, the nature of the effects for predictors is interpreted by the size and sign of the coefficient. In logistic regression, the nature and effect is interpreted by the odds ratio generated from that coefficient.